Hello everyone, my name is Aaryan and today we are here to solve Codeforces around 992 which was rated for Div 2 and took place yesterday. So today we will be discussing the problem number D and E because up till C most of the people were able to solve, and D and E were the problems based on trees, and I think these two problems are more straightforward and easy to implement as compared to coming to a solution for these two problems, as I myself upsolved both of them today, and I got to know that I was just getting into the more complexities of these problems and making my solutions more complex, and even some straightforward approaches are working on these. So let's quickly start with the problem number D. So the problem says that you are given a tree with n vertices and need to construct an array A of length n consisting of unique integers from 1 up till 2 into n, such that each edge uivi of the tree, the value a of ui minus a of vi is not a prime number, and find any array that satisfies these conditions or report that there is no such array. So let's take an example, which is this. So let me just open my OneNote. Cool. Not now. Draw. Not now. Cool. So let's first understand what we are given in the question. We will be given with a tree, and all of these nodes will be numbered up from 1 2 3 4 5 6. So we can say for this tree n is 6, and we have to construct an array such that if we assign values to all of these nodes, this is nothing but a of 1 2 3 4 5 and 6. So we need to assign values to all of these positions such that उन दोनों का जो भी difference होगा that should not be a prime number. So if we are assigning 1 to this value, then we can assign 2 to this second node, because 2 minus 1 is nothing but 1, and 1 is not a prime number. Cool. So we can do that. So can we assign 3 to this node number 3? No, because 3 minus 1 is gonna give us 2, which is a prime number, so we cannot assign this. So in that case, can we assign 4? 4 minus 1 will give us 3, so that's also a prime number. We cannot assign this thing, so we cannot assign 3 to this 4 to the node number 3. Can we assign 5? Yes, because 5 minus 1 will give us 4, which is not a prime number, so we can assign it. So by performing any of the checks and assigning the values to these nodes, we have to give the possible a that can be formed from the given tree. So if we take the example of the very first tree, which is 1 is connected to 2, 2 is connected to 3. So node number 1 is connected to 2, 2 is connected to 3. Okay, and 2 is connected to 4 and 3 is connected to 5. So 2 is connected to 4 and 3 is connected to 5. So this is how our tree is gonna look like. So the very first thing that came to my mind is, if I am assigning some value to any node, I can just assign a value with +1 to any of itself. Cool. So if I am assigning 1 to this node, I can assign 2 to node number 2. But if I am assigning 2 to node number 2, I can assign 3 to node number 3. But in that case, I cannot assign 4 or any consecutive value to 4, because I cannot assure this thing that which value should be applied to this node. So there the solution that I was initially thinking is कि instead of just incrementing a value from 3 to 4, let's increment it by a greater value so that I can surpass the difference of 2 and 3, because these are the major differences that are gonna give us conflict. So for this, if I assign value which is 4 plus 2 6, if I assign 6 to this, I know the difference between my these nodes will gonna be more than this. So after this I can just increment my every value by 2, so 8, then 2, 10. So I know the major number of the major population of these prime numbers are odd. So if I can make the difference between my two values as even as possible, that's gonna save me from getting into any conflict. But due to some conflicts or overlapping issues, I was not able to implement this solution and this didn't pass. But while up solving, I got to know a better solution for this, which is nothing but if we go by a very simple and broad approach, we know from 1 to up till 2 to the power n, we can use any of the numbers belonging to this range. So if we are able, if let's suppose I'm gonna put 1 here, which value can I put here? Now my range is from 2 to the power, sorry, from 2 to 2 multiplied by n, if I put 1 on the very first one. Cool. So इसके बाद हम क्या कर सकते हैं, we can manually check that whether we can put our next node or not. So can we put 2 here? Yes, because 2 minus 1 is not a prime number. Cool. Similarly, my next number will be, if I am just using this range, my next number is 3. So for next node, which is 3, can I put 3 here? Yes, I can, because 3 minus 2 is not a prime number. So now I have to put, let's suppose, any number here. So if I'm gonna put 4 here, and will this gonna give me a conflict? No, I can easily put 4 here. Again, if I come back here and try to put 5, I know 5 minus 2 is 3, which is a prime number, so I cannot put this. Let's neglect this, move on further. 6 minus 2 is 4, so I can easily put 6 here. So by just making or putting an iterator on this range and checking whether which value I'm gonna put here, subtracted by the previous value that I initially put at my parent node. So the value and the value at parent, if this is a prime, I know I cannot put this particular value here. So in that case, I know I have to make my pointer go to the next position. And if this thing is gonna work, I know I can put this value. So just put the value here and move the pointer. And I'm just using a DFS here to iterate over my tree. So let's see whether this solution will work on all the cases or not. So let's take the second example as well. So in this case, node number 1 is connected to 2, 1 is connected to 3, 2 is connected to 4, 1 is connected to 3, 2 is connected to 4, 3 is connected to 5, 6 and 7. So 3 is connected to 5, 6 and 7. So why are we using a DFS? Because we know that if we are putting any value over here, so we know we can just put some consecutive values in the total depth, because we know that is not gonna create any mess for sure. And similarly, the major difference is we are gonna iterate on this value up till and unless we find a position where my value and value at parent is a composite number. Cool. So in the worst case, this can be some larger value, but we know if we are gonna go into the depth, so for any particular depth, in most of the cases my difference is just b1, and will be easily able to put the values here. And whenever I will come back from my this DFS or this DFS call, I know for the second call most probably my difference is larger enough than the initial prime numbers. So there is very rare chance of getting any conflict, and if there will be any conflict, it will be resolved by at most some 2 3 or maybe 5 7 increments. So in the worst case, it will be at almost order of n. And so if we just dry run the, okay, let me just erase all these things back. Let's cool. So this was the initial tree for the second test case. This is node number 2, this is node number 4. Cool. So let's write the range 1 2 3 4 5 6 7 8 9 10 11 12 13 and 14. So these are the total numbers up till 2 to the power 2 multiplied by n. So let's put 1 over the node number 1. So from here I know all of the childs. I can call a DFS for all of the childs, and I know I had used 1. So now I can only put a 2 over here. So let's see whether my value and value at parent. So whenever I am I am at any child node, I know I had already finalized the value for its parent, so उसकी मुझे टेंशन है ही नहीं. So I can easily get this value at parent by using this a of parent and get this value from this array itself, which I am just finalizing over here. So for 1, I know I had already put a value 1 over there. So for node number 2, whether this 2 minus 1 is odd or not, how I am gonna check this whether any number is odd or not. Very first thing is primarily check, but this is gonna cost me root n in the best case also. So instead of this, I can use sieve and can easily generate my all the prime numbers up till 2 into n, and we can store this in any set or map. I am using set here to check whether this thing is present or not in order of 1 or log n, you can say, for the time complexity of using this set. So I can easily check whether 2 minus 1 is a prime number or not. It's not. So yes, we can easily put this value here. Let's increment our pointer, and the DFS call will reach at node number 4. So can I put a 3 over here? Yes, 3 minus 2 is also 1. We can easily put this here. So we will return back from here. The value of this is 3. We'll return back from here. Now my iterator is at 4. So can I put 4 here? No, because if I put 4 here, 4 minus 1 will be 3. It's a prime, and how I can whether this is a prime or not. If this number is present in my set, what I'm gonna do, I will just increment my pointer. So now it's 5 minus 1, which is 4. Yes, 4 is not a prime number. So in this case, I know I can use 5 over here. Let's finalize this. Cool. Similarly, my call will come here. I know now I have a value which is available is 6. Can I use 6? Yes, cool. We can use this 6. Similarly, we'll go back. We'll come at this node. Can we use 7? No, because 7 minus 5 is 2 again. We'll use this 8. 8 minus 5, no, it's 3. We cannot use this. We came at 9. 9 minus 5, yes, 4. So again, we can see for this particular node, we are getting 2 and 3 initially, so we incremented twice. Similarly, for this node, we incremented twice. Incrementing twice or thrice is not a very big deal. So we can do this operation, and I know if I am incrementing plus 2 for every node, and in that case also I'm not gonna go beyond this 2 into n. So for this we had finalized 9. Yes, now my available value is 10. Can I put a 10 over here? No. 10 minus 5 is again 5, which is a prime. Let's move it here. 11 minus 5, 6. It's not a prime. Let's put 11 over here. So this is our array A, which we need to construct, and we had already constructed it. So this is the way that we can solve this problem. Let's see the code for this, and this was the code. Okay, just open up. So I'd also seen this approach in someone's solution from a person who got global rank 30 and all India rank 1 in yesterday's contest, and ये काफ़ी अच्छी approach थी. So what we can do is, this is just taking the input and constructing the tree of size according to the given constraints. After that, I can easily generate primes up to 2 to the power n by just using sieve of Eratosthenes. Now I had initialized my array A. My starting point is 2. Why? Because I'm already gonna put 1 at my 1th node, and this is just a DFS function which is using a while loop, and while the difference of my starting point and the value of it value at parent, it's a odd number, which means it's present in the primes set. I'm gonna increment by pointer, which is st, and whenever I am satisfied that the given starting pointer is not giving me a prime difference, I'll put it my array A, and I'm gonna increment this for the further calls, and then I can make the DFS calls from here. And for every child of 1, I'm gonna call this DFS, because for the initial first node I had already put it this value 1. So after that, just print this a array, and this was a code for problem D. So let's quickly move on to the next problem, which is E. Let me just connect my charger. Cool. So let's move on to the problem E. ये भी काफ़ी अच्छी प्रॉब्लम थी, because initially I was using probability and some expect DP for calculating those expected values, and was trying to and come to a formula which is not getting fitted into the solution. But later on, while solving, I encountered another solution for this, which was pretty straightforward and easy to understand. So that was the main idea behind solving all the contests, that I should be able to come up to an approach which was easy to implement and more intuitive as compared to some or more complex approaches. So this is also a tree based problem, and you are given with a tree of n vertices, and let's place a robot in some vertex that is not equal to 1, and suppose we initially have p coins. So let's make the tree and try to understand the problem statement better. So we will be given with a tree similar to the previous problem, and now this is basically the node number 1. So we will have a robot which will be at any vertex other than 1, and we have some p coins with us. Cool. So consider the following process where the ith step starting from I is equal to 1. So we are gonna take steps with I is equal to 1. Cool. इसको थोड़ा क्लियर लिख लेते हैं. We are gonna take steps starting with I is equal to 1. Cool. So if I is odd, the robot moves to an adjacent vertex in the direction of 1. So if the robot is here, so it will move to this point if the step is odd. Now we have even step. So if I is even, you can either pay 1 coin if there are some left. So basically if you have some coins, you can pay them, and then the robot moves to an adjacent vertex in the direction of the vertex 1. तो हम again 1 की direction में चले जाएंगे if we have some coin. Otherwise or not pay, and then the robot moves to an adjacent vertex chosen uniformly at random. So if we try to understand the complexity of this problem is, let's take some bigger tree. So let's suppose this is the tree, this is our node number 1. So if my robot will start from this particular node, so this will be its first step. So if the step is odd, it's gonna move in the direction which is gonna take him towards the vertex 1 for sure. Similarly, for the second move from this point, it will be gonna be a second move or second step. So if you have some coin, you can pay that coin, and then you can move towards vertex 1. So this is the path which is taking me towards vertex 1. But if you do not have any coin, or you don't want to use it as of now, so in that case you don't have the control to go towards vertex 1, and you can uniformly go into any of the directions, which is basically if the step is even. So and we don't have any coin, or we don't want to utilize our coin, so in that case it might can go into the opposite direction as well. And let's suppose if we are at this point and we are going to take step 2 or any even number of step 2, 4, 6. So in that case, if we have coin, we will go towards our vertex 1. If we don't have coin, so there might be a possibility that we can go from the or to this part or to this part as well. So the process stops as soon as the robot reaches at vertex 1. So whenever the robot reaches at vertex 1, this process will stop, and let v comma p be the minimum possible expected number of steps in the process if we spend our coins optimally. So we need to give the answer for this query or this subproblem, that if we are gonna start from any node number v with p coins, so what is the expected number of steps that will be required to reach node number 1. So expected number of steps is the average or the kind of mean number of steps that are needed to reach to node 1. Cool. So this was the problem statement, and these will be basically Q queries of this kind that we need to answer. So this was the problem statement, and if the answer is gonna be very large, we have to take the modulus with this particular prime number. Cool. So if we take the first example, it is 1 is connected to 2, so total n is 4 and there will be 4 queries. So 1 is connected to 2, 2 is connected to 3, 1 is connected to 2, 2 is connected to 3, 2 is connected to 4 also. So this is the tree itself. So the very first query is 2 comma 0. So we are going to start from this node. This is our v, and we have p is equal to 0 points. So in the first step we are going to move towards vertex 1. So we reach to vertex 1 in just one step. So for this query we know, let's write down the queries here. 2 comma 0, we know our answer is 1. Second query is 3 comma 0, 3 comma 0. So from, let it is this thing. Okay, yes. So from this node number 3, in the very first step, what is going to happen? We'll move to this node number 2 because this is our odd step, which is our first step. हम यहाँ move कर जाएंगे. From this particular node, I don't have any coin to spend. हम क्या करेंगे? We will move to this point. There may be a chance. In that case, 2 moves लगेंगे हमें or 2 steps. But there may be a chance that I will move to this point as well. So for this, how much steps do I need again to reach to 1? Because now the total number of steps are 2. Now I have the third step. Third step हम कहाँ use करेंगे? In this direction. So there might be a possibility मैं यहाँ से ऊपर पहुँच जाऊँगा. मैं 4 steps में भी पहुँच सकता हूँ. But what if in worst case वापस नीचे आ जाऊँ? Or maybe again I can reach to this point, which is 5th step. Then I will be back at this point in 6 steps. So if we are gonna average it out, we know that we can get back to the node number 1 in minimum 6 steps, because I guess this was the answer for this. Yes, because these are the cases that are given to us, and if we are going to average it out, it is 6. So instead of getting into probability thing, because I personally don't like probability, so if we talk this thing in terms of probability, so whenever I am at this position and my step is an even step, so there is a fairly enough chance that I can move to any particular node. So there are total 3 possibilities. So I can go to any of these nodes with this much probability. So we are gonna use this probability with total number of steps that had taken up till now to come to an answer for this, which will be 6. So instead of this, there was some greedy, or you can say an optimal solution which we can choose. So if we try to understand the problem statement more deeply, so let's observe 2 simple patterns and the problem will be solved. Just simple 2 patterns. Cool. So the very first thing is, if our current step or current move is odd, So there isn't any doubt that which path should we take or which path should we follow. We are just gonna go towards our vertex 1, and that is the only step available and the optimal. Cool. But from any particular node which is at our even step, so in that case, if we have some coins, so let's not write it here. So if we have some available coins, what we are gonna do, let's suppose you are at this particular node and you are at this particular node, or let me make it more clearly or differently, that a tree is like this, that it has cool. So just try to understand this thing, that if you are at this particular node and this is your even step, or you are at this particular node and this is your even step, just assume this thing. This is not gonna happen that two consecutive uh, nodes will be your even step, but just assume this thing. So in this case, if you have, let's suppose, one coin, which position it is more optimal to utilize this coin? Just think of it. From this point, how many total deviations or possible paths, or you can say, just say it as deviation, that how many possible deviations are there which will deviate you from your original path. This is our original path that we should follow while going towards our vertex 1 or node number 1. So this is our ideal or optimal path. From this particular point, there are total 1, 2, 3 deviations that will pull me from going to my ideal or the optimal direction. So there are total 3 deviations that will cost me more number of steps if I'm gonna if I'm not gonna use a coin, but at this point. And from this point, the only deviation is coming back to the previous node. So here there is total or at most one deviation. So on, if you have a choice to use a coin, on which particular node you are gonna use this particular coin? On this node, because I know there are 3 deviations, and if I can pass this particular step by giving some amount of coin, that will be more beneficial for me. Because if there is a tree, and let's understand what's gonna happen if we just move back from any node. So let's suppose you came up to this node from some path and you are standing at this point, and this is your even move now. So there might be a possibility that you can choose any of these 3 options. But if you, let's suppose, go to this particular node, this is your odd move now. So what's gonna happen in odd move? We are gonna come back to this node only. Similarly, if you go to this particular node in your even move, now you will be here with your odd move, and you will again go back to your original node. So in most of the cases, at most 2 steps will be wasted to go on any particular node that is not in your path and to come back to your node. There isn't any possibility that you will go into a depth, because whenever you will move to any path which is not on your optimal way, so in that case you will be again restored with your odd move, and you can come back to the original position. So from this point and this point, we know that instead of getting into 3 deviations, it is more beneficial to get into the one deviation and use my coin at this point to bypass this three deviations that just go into my optimal direction. Cool. So the very first thing is use coins at positions which have max deviations. Cool. These deviations are nothing but the number of connected childs to any node. Cool. This is the very first observation. Second thing is, we just discussed it up here that whenever there are, let's suppose, total connected nodes as D. So for this particular node, if my total connected nodes are D, which is 1, 2, 3, 4 in this case, so if I am coming from this particular node and this is my vertex 1, so this will be my ideal path that which I should follow while going towards the vertex 1. Cool. So whenever I will be at this particular node with my even move in my hand, so if there are total 4 nodes connected to this particular node, there is a equal chance to go on each and every node, and I know if I go to any of the nodes which will be taking me away from my path, I will be wasting at most 2 moves. Why 2 moves? We had discussed this thing just here that for any even move, even if I'll move in any opposite direction, I will be at my odd move at that particular node and I can come back to my original node. So for this particular node also, let's erase the unnecessary things first. Cool. Draw this edge back. Yes. So for this particular node also, if we know that total connected nodes are D, so one node will be in an ideal direction. So this is my ideal direction. So one node will be in ideal direction and D minus 1 nodes will be my deviation. So these will be my deviations that are gonna pull me away from going into the right direction. And for every D minus 1 node, I can waste at most 2 moves. How at most 2 moves? That I'm gonna go to that node and will come back again at my original position. So these are the total number of moves that will be added for any node that I cannot neglect. So if we just sum up all the observations and get to a answer, we know if this is our total number of tree, this is our 2, this is 3. Cool. Okay, so let's sum this up. This is our node 1 and we are starting from this point. So this is particular our odd node. I know this will cost me just 1 move because I'm going to go in the right direction, and this dotted path is my correct path that I should follow to reach my node number 1. So from this particular node, this is my even path. So let's mention the total number of deviations from here, which is 1, 2, 3, 4 and 5. So total number of options are 5 from this point. I will be here with a odd number of move. So this is just one move to go in the right direction. From this particular point, I know 1, 2, 3, and 4. There are 4 options, and this is a even number of node, even number or even move node. So I know there are total 4, and let's assume that we have a coin as 1. So I only have a single coin to be used. So again, I will be at this point with a odd number of moves, so I can go towards my right direction in one move. So for every odd move, I know it will just cost me one move to go to the right direction. But for all the other nodes that are even at even positions, I can neglect some nodes. And which nodes I'm gonna neglect? Those nodes which will cost me the most deviation, which is this in this case. So I can skip this particular node and utilize it as just one move by using my coin. Cool. So now I am left with just this thing, and for this has if we assume that let it it's t, I know one move will take me to the right direction, so that will just gonna cost me one. But for all the d minus 1 moves, I know it will cost me 2 moves extra. So for each deviating node that I cannot skip with my available number of points will gonna cost me this much. So this was the main idea behind solving this problem, that we will construct a path from the given node up till, let's generalize this solution on some generic tree, that we are gonna construct a path from our given node to the vertex 1 or node 1, and in this path, if this is our current odd step, I know this is gonna cost me 1 in my answer for odd move. For even move, we can neglect even moves at most coins times, so we will neglect those even nodes that have maximum size of this adjacency, which is the total number of nodes connected to this particular node. So we can neglect as much as we can, and for those which we cannot neglect, we know it will gonna cost us d minus 2 plus 1 plus 1 just okay, so d minus 2 moves and plus 1 will be just for the right direction. Cool. So this was the main idea behind solving this problem, and it can be solved using this. And if we see the code for this problem, cool, it's here, copy, yes. So this is nothing but taking the tree as input, and we also have to take q while taking n. This is a DFS function which is not going to do a single thing, which will be helping us in constructing our path from this particular node to this node. How? So if this is our tree and this is our destination node, or we can say the node from which the robot will start. So what we will do, we will just use a recursive approach. This is our path array. So what we are gonna do, we'll put this one here. So let's say there is another node extra here, x. So we are gonna put one here. If this current particular node that we put here is a part of our path to reaching up till destination, we are gonna return, and if not, we will just pop it out by using a backtracking approach. So again we will reach to this point. This is, let's say, 2. We'll put 2 back. Again we'll put a goat at this point. We'll put x back. For this there is no children, so we know, and there is no children, and this node is also not a part of the destination or not equal to destination. So we will return back from here, and while returning we'll pop it out. Cool. Now we'll go at this point. This is 3, this is 4, and let's suppose 4 is our destination, so we'll reach at point 3, and let's suppose there is another node y here. So when we reach 2.4, we got our node. We will return from this point without popping 4 out. For this particular 3, this DFS call is still running, but we know that at the end of our path 4 is present, which is already a destination, so we are not gonna go more into this DFS calls, and we'll just return from here. For 2, we know we had already get this at the back, we will return, and so on, we'll return back, and this will be filled like this, which is nothing but our path. So that's how this DFS function gonna work, that we are gonna put our node into our path, and if that node is part of destination, we are returning it. Similarly, if during these DFS calls the last node in the path is destination, we are gonna return, otherwise we are gonna keep calling this DFS and going into the depth, and from here we are backtracking simply. So to answer every query, we will get this path, and we are gonna reverse this path, because we will be starting from 4 and will go towards 1, and we can remove this one from this particular path, because from 1 we don't have to go to any node, we just have to reach 1. So we can remove 1 from here, and we know our path is this, that is need to be traced. Cool, right? So for first step, we know it's odd, so for odd we are just going to increment our answer, and for even nodes we are going to increment our answer, as well as we are storing all deviations in an array, that how many total possible deviations are there for any particular even node. So we are iterating on our path array, and for odd step we are just incrementing our answer, and for even step we are incrementing our answer as well and putting it into the deviations array. We'll just sort our deviations array, and we'll remove the maximum deviations from this, and the number of times we have this points. So we can remove the maximum deviations that are possible and just go toward our original path, or the optimal path we can choose from. And for rest of the deviations that are left, we know that there is no other option and wasting 2 moves at that particular deviation node, so we are gonna add it up in our answer. And don't forget to take mod of this, and mod is 29 plus 7 is not here, but it's some other large odd number which is given in the question. So after this, we know our answer variable will be carrying the minimum expected value for this particular query, and we can print this up. So I hope you would able to understand the problem, the idea behind solving this, and the code also. So this was more intuitive and easier to understand solution and approach. That's why I learned this, and also wanted to discuss this with all the people that I am connected with. So that's why I discussed these 2 problems only. So thank you so much for joining, and I will be linking down all the links for these codes in my description of this video. So if you have any other further doubts, do let us know. Thank you so much.